Well, looks like we're just about there, folks. We're just running the clock so far. Any questions while we're waiting? Yeah. We are continuing through 5.4.
Okay.
Really, it's kind of a start. We only kind of just looked at the initial stuff in there.
The next exam will have chapter 5 and 4, 5, and 6, right?
That's correct, yeah. I'm not totally certain about chapter 6, but let's see here. Chapter 6 will probably be doing this week, meaning, yeah, more likely than not. Anything we do on this week right here would not make it to the exam, since the exam is right after. I like to give a little separation so you can get your quizzes done, your homework done, ask questions on the material before just jumping into the exam on it. Those are good questions. Other questions to start us out?
You know that same website you used yesterday?
Oh yeah. I think it was Desmos.
Yeah, Desmos. Are you wanting us to like use that during the quiz or like practice it?
I would say it's going to be totally optional.
Okay.
It's not required at all in this course. And anytime I pull up Desmos, it's only just to give a fast classroom demonstration. So that's usually something that's always going to be optional, I'd say. The major things that we're going to have that are required are just going to be the calculator pretty much. Other questions about Desmos or otherwise? Yeah, that became majorly popular, like I think 5 years ago. It just exploded over the internet. In fact, the student told me about it. That's why I just started using it myself. They just suggested try it out. Yeah, it's just nice for fast computation, fast graphing.
Yeah, it's a graphic calculator, but you can also just use it for regular calculations. And I don't like Apple because it clears everything you do before that. Yeah. For this one, you can see every layer. Yeah, and it saves even when you close the app sometimes.
Well, with our work today, we're going to run through section 5.4. And this is going to be our first section where the calculator is not just a really great idea, it's basically mandatory. I mean, with the standard deviation, you could do that by hand if you have enough determination and your fingers move fast enough. But for the computations we're about to do, that's less a real possibility. Finding the area under that complicated curve is very tough to do, but it's all been coded up inside the calculator. So this will be our major tool. So section 5.4 started off this way. Oh, before I get into that, I did want to mention, if you didn't have your exam returned, come see me and I'd be happy to return it back to you. I've got just a few more that need to be passed back. And if you're not in class today, you can also just send me an email if you'd like, and I'd be happy to scan it and send it back to you that way. Just let me know and I'll be happy to help out. But aside from that, any other questions about the announcements? Okay, I wanted to make sure I mentioned that right there. Okay, well, let's see what we left off on section 5.4. We essentially started this way, definitely kind of confusing, but our goal here was just to see what the role of the parameters mu and the parameter sigma, the mean and the standard deviation, have on the location and the shape of the distribution. But the thing that we majorly observed is, no matter what happens to these parameters, the shape of the curve is always the same, provided you do this on the right viewing window. So if you move mu, the mean to -2, it just recenters it at a location. If you change the standard deviation to 10, all you're doing is you're stretching out the horizontal axis. So we have -30 instead of -3. If you compress the standard deviation 1, data is less spread out. That's why it goes from -0.3 all the way to +0.3. But observe, we're still looking at that same basic shape of the normal distribution. So with that, all that out of the way, the idea with that is, when we go to calculate these things, it is actually pretty tricky to get it in the calculator just right. And even people who do statistics for a living, the PhD statisticians, that's not me. The PhD people, in fact, do these drawings just to make sure all the information is organized the way they think it should be. It's easy to get just turned around with this kind of stuff. So let's give this problem a try first. It says arsenic is a compound naturally occurring in very low concentrations. It's a problem when it becomes higher in concentrations. And they tell us Arsenic blood concentrations in healthy individuals, so not people with arsenic poisoning, can be modeled with a normally distribution. Excuse me, that should have just said normal distribution. That's a typo right there. More of a grammatical issue, I'd say. That should have said with the normal distribution, having mean 3.2 milligrams per deciliter, standard deviation 1.5 milligrams per deciliter. So that's our write-up so far of the problem. Just to take this stuff and put it in our own symbols, I would want to write this out as mu. Oh, let me redo the highlighting. Mu equals 3.2 micrograms per deciliter. Already this is kind of confusing, and it's unfortunate that we use mu, this Greek symbol in statistics, and it's also a symbol used for units. Anyone happen to know what micrograms would really mean here for mu g? Me neither. I think I need to refresh myself on that. Units are not my strong point. It's something like 10 to the power negative 6, I believe, but let's double check that. So I want to go and say microgram once I find the home row. A microgram is 1/1,000,000th of a gram. That's great. Let's see what Wikipedia will give us a good readout here. So mu g is the symbol for a millionth of a gram, 1 times 10 to the power of negative 6. It's a pretty standard symbol, but if you see mu g together, it means we're talking about the unit right here. Mu alone is referring to the population mean. It's a huge conflict in notation. We just have to train our eyes to see it right. Does that make sense, folks, about that unit there?
So that's a mu and a mu, it's not an energy.
It is a mu g.
Okay.
Yeah, kind of a weird unit for sure right here. Usually it's not italicized, so that's one way to tell it apart as well. So when I go to write it, it's best if I write it up here like this. Non-italicized, I think that'd be a better way to present it, just to help out with what is what. So that's our unit, and so it's saying there's 3.2 millionths of a gram of arsenic per liter of your blood. That's what's considered typical, the mean for people's blood arsenic concentration, if you're healthy. In other words, not poisoned by arsenic. The next one is 1.5 micrograms per deciliter. That one will give a value of sigma because it said standard deviation. We don't know the true standard deviation of the population of all healthy people, but this is just our best guess. And we're going to model the entire population with that best guess, 1.5 micrograms per deciliter. So that's just the summary of the problem. It now goes on to ask some interesting questions, which we'll give our best shot at. But really, we're going to treat this as a major calculator problem. So we'll go a little bit slow, explaining why we're using each one of these functions. And first off, it says, what percent of healthy individuals have more than 7 micrograms per deciliter arsenic blood concentration? Include a graph, round to 4 decimal places. Really, this is the place where you want to start. Include a graph. We're not doing what we did in the prior section, where we very carefully wrote out the normal model and what the 6-8, 95, 99.7 rule would predict. This is more just a rough graph to organize the information and show how it goes into that calculator. So here's how my graph would look like for something like this. Something kind of small, nothing major. There's my graph. So we need to paraphrase what this distribution is. We write down n. N comes from the fact that we're modeling with a normal distribution. We put in the first input, the mean, 1.5. I'll drop units just so that it's more compact, easier to read. And a standard deviation, oh, let me try again. The mean was not 1.5, it's 3.2. Apologies to everyone in Penn today. 3.2 and then 1.5. So this is a pretty weird mathematical notation. It's pretty compact, and it's just a way to say the normal distribution having mean 3.2, standard deviation 1.5. So that's just a really fast way to say that. Just to emphasize, this is always the mean mu. Try to write that one italicized to mention we're talking about the parameter. And this one is always the parameter sigma. So the mean comes first. So 3.2, that's the mean so far in the center. And now, well, we included a graph. Let's go back to this part. We want to know what percent of healthy individuals have more than 7 micrograms per deciliter. Let's put here, this is micrograms per deciliter of arsenic, the blood arsenic concentration rather. 7 would probably be pretty far out here. We're not trying to place it perfectly, but just in the right magnitude. It has to be to the right of 3.2. Standard deviation is 1.5, so it looks like it's pretty far to the right. 3 standard deviations added to that would be, my calculator turned off, 3.2 plus 1.5 times 3. So 3 standard deviations to the right is 7.7. So 7 being pretty far on the right tail is about right based on the pictures we've given. So let's put just a little bit more shading here to convey what we want. That is the answer. The shading here is the percent of the individuals with more than 7 micrograms per deciliter blood arsenic concentration. So that's a whole graph. What we now need to describe is how the information goes in. Any questions first, folks, taking the problem and writing it down in this kind of display? Okay, now here's where we're going to decide what's the right function in the calculator. If it says what percent, then we take that and use normal CDF. And normal CDF takes 4 different inputs. It'll take, first in the shaded area, a lower value. So this is input 1, lower. The area we have shaded goes to the right forever, never ever stopping. So that means for input 2, we put in the largest possible number supported by the calculator, 10 to the power 99. Last, inputs 3 and 4 are just the mean and standard deviation that was provided in the problem. So the percentage, or finding the area under the curve, the percent of the area under the curve in this region means normal CDF. And we access it by first doing the following. Let's make this a step-by-step guide since this is really our first real look at this. Step 1, press. Good call, second key. If I get that to type the way I wanted it to. Okay, there we go, second. And bars. So we're referring to these 2 keys right here. Let's get a decent strategy guide going here. I think pink will make it pop. Second key, your color might be a little bit different. And then the bars key, because the second button's in blue. What we're really trying to press is the thing in blue that says distribution. We're looking for the normal distribution, in other words. So that's your step 1 in this process. After you've done the diagram, the graph that we put below. So let's do that right here. Second bars pulls up this display. Now, if we're using normal CDF, because we're looking for area or a percentage, we need option 2. So go down to option 2 and hit enter right as the calculator looks like this, option 2 highlighted. Let's make that our step 2. Step 2, let's say, select normal. Let's make it the same the way it's presented in the calculator. Normal CDF written that way. So you'd be selecting that option and pressing enter. There we go. Let's put there here and press enter. So once we get to this page, here we just go back to the diagram and fill in the information that we've indicated. So let's say here, step 3, use the diagram to input the information. Now, this is where it could be a little bit different for a lot of folks. Depending on how old your TI-84 calculator is, you might not even see that screen. It could look a little bit different. Also, if you have a TI-83 calculator, the screen could look a little bit different too. So I'll show how that all looks with a TI-83 after we run through this, just in case someone's using an older TI-84 or the TI-83. But when it says use the diagram to input the information, it means we go back over here. When it said more than 7 micrograms per deciliter, that meant 7 was the lower bound. So for lower, throw in 7. There is no upper bound. They would have said from 7 to 10 micrograms per deciliter if there was. In that case, we would have put 10 here. But if they just say strictly more than, that means we're not stopping at all. And we put in 10 to the power 99. Looks like this in the calculator. Go 10. Then above your division key is the exponent key. It looks like just an up arrow, 99. So that's the biggest number you can throw into the calculator without a syntax error. That sort of approximates this area exceedingly well. And the nice thing is there's no thought. You don't have to worry about is 7,000 long turn up as a number. That depends on how large the standard deviation is, for example. Finally, just plug in your mean, 3.2, your standard deviation, which is 1.5, and your calculator should look like this at that step. So let's do this as our final step here. So step 3, use the diagram to input the information. And then step 4, we'll just simply say, press enter a bunch of times. And that gets you right where you need to be. So let's do that. You enter, oh, hang on, I didn't want to hit that. Let me clear that out. That was a 1.5. There we go. Hit enter when it says paste. I think you're okay if it looks like that for you. Hit enter there, and something weird comes up. Just a weird comma separated thing. This is what it would look like if you had a TI-83 or an older TI-84 that didn't have the update. But on this line, all you're going to do is press enter again. So that's why we just said a bunch of times. And that's your answer, 0.00544649. Let's put that down just to show this is what your calculator should look like at that step. Any questions, folks, on getting to that number? Okay, well, let's go back up to the problem just to answer the question. So back up in the problem, well, it asked for what percentage. This is where the instructions can be a little bit vague, especially with rounding. That's not a percent, that's the percent converted to a decimal number. So you want to hit times 100.
0.56%?
Exactly, yeah. Shifting the oh, what did I do? That was an error somehow. Oh, I didn't have the prior answer there. Let's go up times 100. Or you're just shifting the decimal place 2 spots to the right, like you mentioned. Let's make the calculator do it for us. It was expensive, so we might as well put it to work. So there it is now as a percentage. We want to round the percentage to 4 decimal places. Exactly. 5, 6, yeah, 4, 9, rounding down. So that's our answer, 0.5649. It's good to kind of convey what this even represented. This is for full credit on a problem like this, whether it's a quiz or exam problem, but on the notes, I'll often write this out. There's a 0.5649% chance.
Why do we have to have 4 spaces? Pass it in. Because the problem's asking included and round to 4 decimal places. Oh. Okay.
Yeah.
I missed that part.
Honestly, this was if I'm thinking about this problem, I had it from a different book, and the book said, what probability? In which case, you would have taken this number rounded to 4 decimal places, this one right here rounded to 4 decimal places. Answer would have been 0.0056. Then it would turn into 0.56%. But I forgot that this was asking for what percent. And so when it's what percent, we have to convert to a percent again. I should have said round to 2 decimal places, honestly, to make it more compatible. Just totally forgot.
So the probability is what is just 0.0056 and then rounded in
Yeah,
0.56%.
exactly. But in this problem, we converted to a percentage, then we rounded the percentage to 4 decimal places. I think more typical is to 2 decimal places, but we just have a little extra precision here. Gotcha. Other questions about that? Okay, so there is a 0.5649% chance, like 0.5% chance, that a healthy person has more than 7 micrograms per deciliter blood arsenic concentration. That's highly unusual since it's almost 3 standard deviations away, and that's why the percentage is so low as well. But any other questions, folks, with finding that value? Awesome. So this is now using a pretty heavy lifting calculator to define these areas. It's doing a lot of weird things by approximating this area, but these kinds of questions can be confusing because what's changing is sometimes the lower value is not a number like this one. Maybe it's negative 10 power 99. Sometimes the upper value is something other than 10 power 99. And sometimes you're not using normal CDF at all. So part of our goal in these notes is to say, when are you using more normal CDF and when are you using something different? We'll always kind of indicate in the problem why we used one function or the other. So let's try this again. Down below, they're asking a follow-up question. What percent of healthy individuals have less than 3 micrograms per deciliter blood arsenic concentration? So let's start off with a quick graph. This is our way to organize. And on a real exam situation, it is really easy to put information incorrectly in the calculator. But if your graph right here looks correct, you do get a lot of partial credit. So it's my way of also giving partial credit by putting in these instructions here. That way, I'm not just looking at a number and taking off 4 points or awarding all the 4 points. There will be a fudge factor. In other words, if you're putting it all together here, get the wrong number, I'll just assume you made a mistake in the calculator, but you understand the concept, giving you lots of partial credit. So let's write out the model once again. It's N for the normal distribution. I believe it was 3.2 for the mean, that goes in first, and 1.5 for the standard deviation. Now here they said less than 3 micrograms per deciliter. So let's start by putting in the center is 3.2. It's always a good idea to put that in there just to make sure when you're taking this, you're putting it in the right relative region. So it's got to go to the left, but the standard deviation is pretty big, so it's actually close to 3.2. I'd probably plot it right about here. So here's 3. Now this says less than 3 micrograms per deciliter. It means we're shading to the left. So let's say that right here, just for a paper trail in the notes. Shade to the left. So here's our shading going this way. Kind of lazy shading, but it does the job, doesn't have to be perfect. Now, if the question was less than 3.2, well, that's directly in the middle. We would have said a 50% chance. So just by doing this diagram already, you can get a good idea if your numbers are even in the right ballpark. If I get a number of, say, 63%, we're way off. It should be below 50% with where 3 is. But from this and just instructions right here, what percent, this alone tells us once again, use normal CDF. CDF once again just stands for cumulative distribution function. You don't have to memorize that for the notes or anything, but the reason to mention it is when you say cumulative, you're just talking about accumulating all that area. That's what the function's trying to do. So like before, we have to say what goes into the calculator, but any questions with the diagram? Okay, well, input 1 is always the lower value. But observe the shading on this one. If it's shading starting at 3 and then going to the left, it means it's going to the left forever. We had no stopping point. So the lower value is negative 10 to the power of 99. So this time we're using our largest negative supported number in the calculator. This is input 2 for the upper. What we mean is upper bound. In other words, when we look at the area, there's a boundary right here, right at 3. So that's our upper bound, input 2. The last ones are easy. That's always the third input and the fourth input. And the calculator helps. They say what symbol each one of these should be to indicate. So that's our setup so far. We'll just repeat the step-by-step instructions we saw here on the last problem. It starts with second key and the bar symbol. Then go down to normal CDF and enter on this one. We have the prior information, so we just need to change to -10 power 99. But watch out for this in the calculator. You can't use the negative symbol. That requires 2 numbers being subtracted. You need to use that one down there. Otherwise, you'd get a syntax error. So go negative sign, then 10 power 99.
10 to the power of negative 99.
Not negative 99, because that would give us a number close to 0. So we would have to have a positive 99 there. Other questions so far? Okay, so now for upper, that one's totally wrong. Our upper is at 3. So just hit 3 there. And for the last 2 values, we have exactly what we need already. So it's kind of nice the calculator remembers these things. Instead of this complete step-by-step guide, I'll throw in this screenshot to show what your calculator looks like, should look like before hitting enter. So everyone's calculator should look about like this. Once we hit enter, several times, that's a percentage we get, or excuse me, well, it's a proportion right now. The problem wants a percent, so let's hit times 100, essentially just doing a decimal shift. It wants it rounded to 4 decimal places, like we mentioned. That is a lot. I think if I thought about these instructions, I would have said 2 decimal places. But you know what? Let's go with it. Might as well, it's good rounding. 44.6965.
You only round the last number.
The last number right here?
Yeah, so you said it's 6965.
Yeah, exactly. So the thought on this one is, if they say 4 decimal places here, you go over to the 4th place.
Yeah.
Then you compare the number to the right. About 5 just means round up, but it's only that number with the arrow that's changing.
Yeah.
Exactly right.
You don't have to change the rest. That's why.
You sometimes do if it's say rounding with carry, and that gets really annoying. So watch out for those. Other questions at the moment? Okay, so with that number there, let's just say what it means really quick, since it's easy to get a number. It's hard to say what does a number really represent. And we'll do that a little bit more in the actual probability chapter. For the moment, this is for full credit, just saying the number. But let's say there is a 44.6965% chance that a selected, let's say a randomly selected healthy person, we're saying healthy person since that's the overall population we're concerned with, has a blood arsenic concentration below 3 micrograms per deciliter of blood. So that's our interpretation on that one. Looks like it's relatively common, but it should be since the number in question was very close to the mean. If it was less than 3.2, that would have been exactly 50%. Well, any questions, folks, at the moment with these 2 computations? Okay, I forgot to do one thing with other people using, say, the TI-83. So if you have a TI-83 or a calculator very similar to that one, this is what the actual inputs would look like. So let's open up. How do we do that? I forget. File, open. There we go. That does the job. So this is the good old TI-83. It's kind of a nice calculator. I think I prefer this one, but it doesn't have as many creature comforts. It is even missing a couple statistical functions, but we have a workaround with that. If you're using this calculator, you're still just fine in this course. So in this calculator, you'd want to hit second. Let's first turn on the contrast. This is kind of dim, actually. Is that readable on the projector? Oh, probably better up there than on my screen. So first thing you hit is second bars, just like before, to access the distributions. Then you go down to normal CDF. So far everything is similar. But this is where it gets weird. You just have to know the order everything goes into the calculator for this. And that's why I'm putting these instructions on input 1, 2, 3, and 4, just to support more and more calculators. So input 1, negative 10 power 99, we just type it in. Up arrow above the division key to get the exponent. And now for input 2, you have to literally put in the comma. It's right here above the number 7. So there's your comma. Input 2 is a 3. Another comma. Now we're putting in the mean, 3.2. Comma again, and finally 1.5. So in the TI-83, this is what it should look like. Hit enter, and we get the same value as before. So let me put that down as just an extra screenshot. For TI-83 calculators and calculators very similar to it, your input probably looks like this, something along those lines. Well, any questions, folks, with either calculator? Okay, let's go to the official one then. And by the way, for folks using the TI-83, if at any point something goes wrong or just doesn't look quite right, if you'd like to see it redone on the TI-83, don't hesitate to ask. I'll be very happy to show what that would look like. Well, looks like we have one last question to run through. Let's move that down. This one says, what blood arsenic concentration describes the 25% of lowest blood arsenic concentration in healthy individuals? So we want to find the cutoff for the 25 lowest concentrations of arsenic in people. Well, notice that there's something weird about this problem. It gave the percentage. In the other problems, we were looking for the percentage, but this one gave it to us. What's missing? The value on the horizontal axis is what's missing. And so if a problem ever looks like this, where a percentage is given, actually, let's make the bracket go right here, where it's just the percent we're looking at. We have to use inverse norm. So it's a whole different function in this case. Again, the way you can tell is the problem feels backwards. It feels like they gave you the answer, but you don't have the question. And that's why it's called inverse norm. We're literally doing the problem in the inverse way. Well, it still asks for us to include a graph, so let's start there. Here's a graph. Kind of a lazy one, does the job though. Forgot to put on the x-axis a description, so let's do it on this one. This is blood arsenic concentration. I'll just abbreviate concentration to consent. And for normal distribution with a mean of 3.2 and a standard deviation of 1.5. Okay, so there's our model so far. Like before, we have in the middle 3.2. And now we want to start bringing in the information provided right here. It said 25% of the lowest blood arsenic concentration. So we want to put a cutoff somewhere that captures 25% of the area to either the left or the right of that cutoff. Well, my question for you is, they say 25% of the lowest, would our cutoff be here or would it be here, the left or the right? Good call, it's got to be the left. So let's go here. We're trying to solve for some unknown quantity. You could call it X if you like, remind you of algebra. Call it K if you prefer, really just totally up to you. Let's go with X. I don't have X in the most perfect position, but my eye, with what I see here, that looks like it's about 25%. That's already kind of tricky in the calculator. Let me put in some extra space. One issue with the calculator is it will not accept a percentage. It will only accept a probability. Well, so we convert this just by taking the decimal point, shifting it 2 spots to the left. That's too many spots. So you have to use 0.25. Let's make that as a note right here. Convert to a decimal. That deserves an exclamation mark, and you'll know right away something is going wrong. If you put in 25, you'll just get an error for this kind of problem. So 0.25 is going to be what's described right here for that area. Looks like that's the whole picture so far. Let's just describe what goes into the calculator. Any questions whatsoever with the diagram? Okay, well, inverse norm is an interesting function. It only takes 3 inputs. Input 1 is going to be area to the left. Let's underline that. This deserves a lot of emphasis. This calculator only accepts area to the left, and this is where it kind of just depends on the model of calculator you've gotten. There's some TID4 calculators that have extra fancy graphics on it, so it might look a little bit different there. We have more options, but most people's TID4 plus, it's this model here, you're limited to only having area to the left. So luckily we have area specified to the left on this problem. We'll see in the next example what to do if it had area to the right. So input 1 is going to be 0.25. And finally, input 2 is the mean. Input 3 is the standard deviation. So that gets us started. But this is our first time using inverse norm, so let's show in the calculator what this would look like. Whether you're using inverse norm or normal CDF, it always starts off the same. Hit the second key, hit the vars key, and then pull up the right function. So for this problem, you need inverse norm here. Let's say for step 1, we're selecting this function. That's skipping a prior step 1, but we know we always hit second vars to get to this stage. So step 1 for this problem will be select this option. Select inverse norm. So once that's selected, hit enter on that. You have to give it the area, 0.25. The mean, didn't remember, but it's because it's a different function. Normal CDF would have remembered. So 3.2 goes here, and 1.5. So this is your step 2. Yeah, it looks like you have a different kind of calculator. So if you have something that says tail, you're either going to be using the left tail, if your picture looks like this, or your right tail, if your shading was to the right. Exactly. So we're using that model there. So different models of the TID4 Plus have slightly different screens for that reason, but you're going to get the same exact results.
So I just do the left tail, because we're doing the left area.
Exactly, yes. Well, with that put up, with this slightly older version of the TID4 Plus, that's about what your screen will look like. Any questions at the moment? Gotta say what the step is. This is step 2. Not letting you select the tail.
Oh, okay.
I'm glad more than one person has that calculator. That's awesome.
Yeah.
Down arrow to move to the next option as well.
Yeah.
Awesome. Just in case I have more students with that calculator, it's good for me to know as well. I should probably buy one of those at some point. So step 2 is, depending on your model calculator, of course, input information in this form. Then press enter a bunch of times and you're all set. So pressing enter on this, let me know if you're getting some different numbers. Oh, I wiped out my 1.5. In my calculator, it looks like this first. Hitting enter again, we get that value there, 2.188 and some change. So this isn't really a step, just more a result. Let's call this success. everyone's calculator should be giving you that number there. Might look a little bit different on how you got there with inverse norm. But let's go back up here, record our result, and notice the diagram helps a lot because if my value wasn't 2.1, if it was like 5.6, immediately we know something is wrong. X had to be less than 3.2. So it says here, round to 2 decimal places, which is appropriate for one of these values. We'll say X equals 2.19. But this value has units this time. It's not a percentage. This has units of micrograms per deciliter. So that's the total answer. If you left off the units, I'm not too worried about that. But you could also think in these terms. X equals 2.19 micrograms per deciliter describes that 25% of lowest blood arsenic concentrations in healthy people or individuals. People is just faster to write. Well, any questions, folks, on finding that value there? Okay, so far, these are the major functions that we're using in the calculator. But one example like this doesn't really contain all of the little nuances that can come up with these kind of questions. So we have a follow-up question of doing more of this kind of practice. And also, maybe just for the sake of, again, if anyone has the TI-83, let's just show this one more time. So let me open up the good old TI-83. It kind of looks like an old calculator by modern standards. Still does a good job. It still costs like $100 for some reason. If I could hit second, bars like before, go down to the inverse norm option. And like before, it's pretty Spartan as far as a calculator goes. We just have to know the input order. So input 1 is the area, but always watch out. We never put in the percentage, can put in the decimal, 0.25, hit your comma, and now put in 3.2. Good news is the mean always comes first. The standard deviation always comes last. And that's because the people who designed the calculator were probably using that notation themselves, putting n mu sigma in. So lastly is 1.5. Close the parenthesis, hit enter, and you get the same value right out. Well, any questions, folks, with using that calculator there? Awesome. You know, I actually kind of like this calculator more because it doesn't have a scroll bar. If you go to a new line, you can see your whole thing on one line. With the TI-83, you have to scroll left and right to see your entire input. Sometimes that's actually really tedious. I don't know if that's an option you can change or not. Probably not. Well, in all honesty, I haven't looked into it. Maybe there is a way to control that. But let's just say here, for the TI-83, your input should look like this. Oh, I thought I got a screen. Oh, there's 2 of them. I guess Microsoft Word lagged there for a moment. So that's using the normal distribution, using a calculator to power through the computations. And that means the last section that we just went through, it's kind of weird to decide where does this information fall? Normal models. Well, it's possible that these could be quiz or exam questions. You might have to do something like these problems. Given data, assess where the normal model could be used or not. Say for this example, absolutely not. The data is far too skewed. And you could also potentially have a question where you're doing something like this, but it's not going to be too majorly emphasized on the exam. As far as this material goes, this was more to give us a picture in our mind's eye so that when we go to actually draw these out, we know about what it looks like. And when we put the information in the calculator, we're putting it in an accurate way. And again, there's a picture in our mind, so we can just decide, or is our output even reasonable? Without having any of these pictures, no idea if 2.19 makes sense. It's just what the calculator gave us. So this gives us more accuracy in preventing errors. So again, section 5.3, still important, but it won't be a major emphasis on the exam. I think the major things we'll look into is deciding if we can use a normal distribution or not. Well, let's give another problem a try, but any questions or comments at the moment? This will be our last one for the day. Example 3. Looks like this one has to do with alcohol. It says here, a machine that cuts corks for wine bottles operates in such a way that the distribution of the diameter of the corks produced is well approximated by a normal distribution. So of course we have to have that, or it wouldn't fit in this section. We have a population mean of 3 centimeters. It's a good time to start recording information. In our language, we would say mu is 3 centimeters. We have a population standard deviation of 0.1 centimeters. And so that's our value for sigma. So that's the breakdown of the problem so far, finding the parameters. And here's where the question starts. They begin by saying the specifications of the wine bottle call for corks with diameters between 2.9, 3.1 centimeters. So it doesn't have to be perfect for the cork to work in the wine bottle. So there's some tolerance in there. We want to know what percentage of corks produced by this machine so that where these parameters are accurate values have the required diameter. In other words, if the machine really has a mean of 3 centimeters, standard deviation of 0.1 centimeters, how many of those corks can you really use? We would hope like 90%, right? That way there's very little waste. But if we can only use, say, 30% of those corks, maybe the machine should be retuned so that we can really use it for the wine bottles where the fit has to be between those centimeters. Well, like before, we want to include a graph that specifies the information. But from right here alone, when it says what percent, are we using inverse norm or normal CDF? Anyone happen to know? Good call. Any question about a percentage is normal CDF. So from that statement alone, normal CDF. Good call, Courtney. That's definitely the normal CDF on this one. So normal CDF. And it's from that part of the question that indicated the function. So, well, with either function, we're always drawing about this shape of a curve. So here it is again, not my best work on that one. But honestly, you want to avoid that where it touches the x-axis. Not because you'd lose a bunch of points on this problem, but it could misconvey what you're trying to say. So let me just scoot it down a bit. Now this is n for normally distributed, 3 for the mean, and 0.1 for the standard deviation. So Courtney says, if it says less than, it's negative and inverse. Not in this kind of case. What would make it an inverse is if the problem looked like this instead. If it said something like this, where they gave you the percent in the problem, and now you're looking for an x value along the horizontal axis, that's the time you'd be using inverse norm in this kind of situation. Looking through the problems, if they say 1%, that's definitely normal CDF. This one says, let's see, what percent again? So normal CDF, but it's that question right there, part C. They gave us a percentage here. So just purely based off that.
So every time we're given a percentage in the problem, it's going to be inverse.
Exactly. So the percentage right there means use inverse norm. Absolutely. Thanks for asking about that, Courtney. Honestly, that's one of the more confusing things about these problems. There's 2 functions you have to use, and you have to know the reason to use each one. Other questions so far? Okay, well, let's complete the model. We have a value of 3 right here in the middle. Next, we go to the question. It wants diameters to be between 2.9, 3.1 centimeters. So we'll go to 2.9, about right here. And then 3.1 is about right here. This is the diameter in centimeters. But notice, if the standard deviation is 0.1, and we went off to 3.1, that's 1 standard deviation to the right. That's 1 standard deviation to the left. I'll delete this in a moment, but just for the sake of tying back in the last section, Anyone remember the approximate percentage in the middle? Good call. So our answer should be close, very close to 68%. This is our opportunity to see just how accurate was that approximation in the first place. Our calculator will be far, far more accurate. So this is what the shading will look like then, finally putting those values in. Once I get rid of those things. We're going from 2.9 to 3.1. We want all this area, this time in the middle. So this is a little bit different than the first question we did before. There's no 10 power 99 or negative 10 power 99. What we have instead is, that's input 1, the lower value. That's input 2, the upper value. And that's input 3 and 4.
2.9 is the lower and 3.1 is the higher?
Exactly, yeah. Well, sorry if I said that backwards. So yeah, 2.9, it's the lower end where the boundary is for the area. And 3.1 will be the upper end. So let's give this a try. The mantra is, this time, not the stat key. We want to hit second bars, pull up normal CDF. You could just hit the number 2 and it pulls it up as well. Sometimes it's a little faster. Lower bound is right where the area starts, 2.9. Upper bound is exactly where the area this time ends. So we have an ending and a beginning this time. And now mu is 3. Sigma is 0.1. So that should do the job for us. Enter a whole bunch of times on this screen. And this is the area we're going for. Recall we were expecting 68% by the 68-95-99.7 rule, but now we have just a little bit more accuracy. That's kind of nice. Still weird rounding on this, round to 4 decimal places. So first thing we'll do is convert it to a percentage. Shift the decimal or just multiply by 100. And to 4 decimal places, again, that's a bit awkward. If I was asking for a percentage again on a real quiz or exam, I'd say to 2 decimal places. But following those instructions to the letter, we would get 68.2689. Now you have to wonder, is this good or bad for the company? I'd say probably bad because you're wasting a lot of corks. Under 70% of those corks could actually be used for the wine bottle because they have to be between those two specifications. And that will only happen that percentage of the time. So we could say here, 68.2689% of all corks produced will have diameters between 2.9 and 3.1 centimeters. Kind of concerning for the company. But any questions, folks, with the conclusion to part A? Okay. Well, part B is an interesting follow-up question. This one could be a pretty hard one because it's asking for the following: a cork produced by this machine that has a diameter smaller than 2.9. We're talking about this region now, or larger than 3.1. We're talking about the other region over here is considered defective. That makes sense. They told us the wine bottles has to be between 2.9 and 3.1. So smaller than can't be used. Your wine will leak out. Larger than, well, if you try to cram the cork in, you might break the bottle when the machine presses it. So those are definitely defective. But we want to know what percent of corks produced by this machine are considered defective. Include a graph round to 2 decimal places. This is still a normal CDF problem, but we don't actually have to use the normal CDF. So let's think about this one as we're producing the graph. So what percent? Just because of conveying what you would use, this is normal CDF, if we decide to use that function. Here's what the graph looks like. Essentially like the one above, except I'm going to shade where it's highlighted in yellow. So it's N 3.1, like before. Forgot to color code those. We'll just slap it with a highlighter. Just to remind ourselves of the context, the x-axis is diameter. in centimeters. Here's a center at 3, and it says, we want to know what percentage of the machine corks are defective. It's defective when it's smaller than 2.9. So here's 2.9. Smaller than means shade to the left. So we want that area. Next, it says larger than 3.1 centimeters. Because of the statement of larger than, we're shading in this direction next. And my claim is, you don't actually have to use the calculator for this one. Anyone happen to know the trick to find the area?
You know, the 2.9 is 68%, just subtract 100 minus 68.2689.
Exactly. You don't really have to work too hard on this thing. The total area is 100%. And it's because on that problem, we had the area in the middle. In this problem, we want the area in the tails. These are complementary regions. They add up to 100%, like you mentioned. So good call. This would be working far, far more efficiently. Well, that's the real purpose of part B, to show sometimes you can just use your prior computation to make the next part easier. That's something that could happen in the homework as well. So let's write down, as you said, take 100%, subtract the prior answer. This is an interesting enough step that I think we should do some highlighting. We're trying to get that area, which is conveyed in here and here. So we're subtracting 68.2689. Instead of retyping all that, you can go over here in the calculator, just turned off. Go 100, hit minus, and go second, a negative sign for prior answer. That gives you the percentage we want, so 31.7311 after rounding. Does that make sense to folks on how we got that complementary percentage right here? Okay, later on when we're in the actual probability section, we'll call that the complement rule for probabilities. Total probability is 1, same as the 100% we're doing right here. And if one question complements the other in this way, then you can always have a really shortcut for running through the problem. So we can say here, 31.7311% of the time, or of the corks, produced are defective. Stepping back from the problem, this one said 68.2689% of the corks actually work. They're between 2.9 and 3.1. So the complement of that percentage, just taking 100% minus the answer, tells us the percentage of the corks that will not work. So in a certain way, you can think in those terms, and you may not even really need the graphs to get to that last conclusion here. Well, any questions, folks, with the write-up on this one?
When we're doing graphs for these problems, do we always have to write n and then the median and then again the sigma?
I would say no, not necessarily. I'm mostly putting it on the paper here, just as a reminder that that's input 3, input 4. If you come back to these notes, that's like the paper trail of how we input in the calculator. If you left it off, I'm not so worried about that. So if your graph looks like, say, something like this, then it's got the right information. I wouldn't be too worried that even if you didn't put it in the center, you just have the relevant information from the problem, you still have a great graph, I'd say. Other questions so far? Okay, well, looks like we have one more. Let's give this next one a try. Part C asks, what cork sizes describes the 1% of largest diameter corks produced by this machine? So we're going way beyond 3.1 centimeters. We're in the defective range again, but still we want to know how big are those corks? So because they gave us a percentage once again, this time we're using inverse norm. This is where the methods kind of deviate depending on your model calculator. It's a little bit weird teaching statistics sometimes. The calculator isn't fully standard. In the calculator I use, this inverse norm function only produces, or let's say only calculates with areas 2 the left. And that's for this model calculator that I'm using, the T84 Plus, probably the more common calculator among students in the class. Let's underline that again because that comes in full effect on this problem. Let's start by just writing down the model. Here it goes. N3 and 0.1. Okay, so we've got the model indicated there. Now, because it said largest diameter corks, we're taking the 1% and putting it on, this time, the far right tail. If it said smallest diameter corks, we would have put it in the far left tail. So let's draw this out maybe a little bit further. Put a value here, call it X, K, A, B, anything you like. I'm a fan of algebra, so I'll call it X to remind us we're solving for X really in this kind of problem. And this area I'm shading right here, we actually know it's this value. We take the 1% that was provided. We can't actually work with 1%. We convert it to a decimal. It becomes 0.01. And that's the area that goes inside right there. That's not the input to the calculator, though. That's what's really kind of frustrating. Depending on your model, I think you said your model was the T84 plus CE edition, something along those lines. If you're using that model, let's say here for the CE, I'm not sure what that stands for, but for the CE edition. What's that?
That's what it said in the notes, so I thought it was the CE.
Gotcha. The CE does just fine. I think I left it unspecified, just T84 plus, but then there's loads of different versions of that one. So for the CE edition, use the right tail, and it would be just fine. Why right tail? Only because it said largest diameter. But that doesn't work in this T84 plus, so we have to specify the strategy in that case. Our T84 plus, if you're using this one, only produces area to the left. So my question now is, if it's 0.01 right here, what goes right here instead? Exactly. Not too different than what we did in part B. This has to complete a whole. You can either call it 100% or an area of exactly 1. We're using decimals, so we should go that route. The value that goes right here is going to be 1 minus 0.01, which is equal to 0.99. And that's the area in this region. So 0.99 is the area to the left. Let's underline that right there. So 0.99 goes there. Let's maybe just write it once more, just to emphasize. Then that 0.99 is input 1 in the calculator. The mean of 3 is input 2. Standard deviation of 0.1 is input 3. Now, it seems like this is all really, really dangerous and finicky, but it's actually not as bad as it seems. Let me put it in incorrectly to show you how to spot if it's been a mistake in inputting the result. First, I have to turn on the calculator, hit second bars. This is an inverse norm problem, so you can hit number 3 or scroll down and hit enter. Now, suppose I just made the mistake. It's so natural if they give you 1% to put in an area of 0.01. So let's just say we did it. This is wrong, so don't make this the official part of your notes. You still put in 3 and 0.1 like before. And here's what will happen if we put in the wrong area. We get a value of 2.76. Why is that wrong? Where would you say in the diagram spot can we really see that that's the wrong value? Exactly. Our X value here could never be a 2.7. It's got to be like 3.7 or something like that. So it tells us we have the totally wrong value. That's okay. We just go back, hit second vars, go back to inverse norm. So if 0.01 didn't work, this was the problem. It only accepts area to the left in this version of the calculator. So you would do this, 1 minus the 0.01, put in the 0.99, the complement probability, Same values below will do the job. And here's what you would get at that stage. 3.23, and that's what we're anticipating on this one. So the way your calculator should look like on this one, let me go back to that screen, is like that. Now, if you're using the CE edition, if you select the left tail and 0.99, you're doing it exactly the way we're doing.
So mine says 0.67.
Oh, interesting. Let me take a,
Bar, normal.
just taking a quick screenshot here. Kind of tricky, actually, yeah. Honestly, it's tricky whichever calculator you're using. So people with the 1084 Plus Ordinary Edition have some difficulties. The CE Edition has its own set of difficulties. But that's why we're going slow, practicing these all out to see how they go. So let's take a look. So yeah, at the end, your output should be this. Appreciate the support in the class with a different calculator. Could be your mu and your sigma potentially. But let's report the answer. X equals 3.23 centimeters. This describes, let's say X equals 3.23 centimeters or larger, describes the 1% of largest quarks. All of them defective, since that's, again, way above the 3.1 where the quark could be usable. I see. That could have done it. Other questions at the moment, getting these values to come out? Okay, there's very similar questions that you'll see in my stats lab. Again, think of all this as we're practicing in the classroom, extra practice in that my stats lab. And by the time we get to the point of doing this on the exam, this should become really second nature. So the more you practice in class and the homework on quizzes, the more it all comes together. But even on the exam, you can come back to here and record these kinds of step-by-step guides, just so maybe you might lose your way on exams. They're stressful, but this will be extra protection on your note cards or your sheet of notes. Well, when we come back next class, we're going to take a look into the next chapter. But any questions at all, folks, before we call it a day officially?
If we were to answer that as like X is equal to greater than and equal to 3.23 centimeters, would that still be a valid answer, or do you want it to be 3.23 or larger?
I like the greater than or equals. That would work great. That's a great shorthand to writing this out, conveying the same information. So that'd be perfect. Other questions? Okay, well, have a great night, folks. We'll reconvene on Thursday. It's kind of weird going Monday, Wednesday, Thursday. It feels like a lot of work all of a sudden, but we'll get through it. I think this campus just has an aversion to Fridays. I don't know why.
What? I don't think go through on Friday night. Yeah, but I have a friend that has a class Friday nights here.
Oh, wow. And Friday as a night class is extremely rare.
Yeah,
Great parking, I guess.
yeah.
Thank you. Have a good one.
Yeah. That was a lot.